Okay, hi everyone. Welcome to our first Cosmic Conversations talk of the second semester, and our fifth one in total. And today we have Devon, a second year master's student, who's working with Professor Weigel, and he's going to talk to us about particle physics in a very small nutshell. So, yeah.
Cool. So this is basically what I'm going to go over. Yeah, so pretty basic stuff. So the idea that matter is composed of elementary particles can actually be dated back to the 6th century. However, it was only in about the 19th century that any real progress was made. And this started with a guy called John Dalton and his atomic theory. And this was mostly used in chemistry, but this was the basic idea for initial particle physics. Obviously, the third rule is wrong. So after this, in about the 20th century, beginning of the 20th century, a man named J.J. Thomson suggested that the particles actually, or the atom, was actually made of electrons embedded in some positive charge, a ball of charge. So this was called the plum pudding model. Then after that, from 1908 to 1913 was Rutherford's experiments over here. So Rutherford shot alpha particles at a thin gold foil. The idea was that if Thomson's theory was correct, there should be little to no deflection through as the alpha particles pass through the gold foil, and it turned out that this was incorrect. What happened was that alpha particles actually went and experienced violent collisions, and this resulted in very large scattering angles, as you can see on the left picture. So Rutherford suggested a new type of atom, which had a nucleus, a massive localized nucleus at the center with positive charge, and then electrons somehow orbiting around it. And then through theoretical calculation, he confirmed that this was the case, and this matched experiments. After this was, this proved the existence of the nucleus and hence the existence of the proton. Later then, the proton was actually isolated in the laboratory as well. So then from 1932, somewhere in 1932, a man named Carl D. Anderson discovered the first antiparticle. So, and that was the positron, which is the antiparticle of the electron. Let's just go to the Rutherford model there. So the way they discovered the positron was they were studying cosmic ray collisions in a cloud chamber. And then initially what they thought was the positron was just some sort of electron moving in the opposite direction, until they discovered that wasn't the case. Then further on in the 1950s and the 1960s, a variety of other particles were discovered. This was using higher energy collisions and colliders. So this includes other antiparticles, and this all these particles being discovered was initially called the particle zoo. And then, first I have to kind of describe what an antiparticle is. So the idea of the antiparticle is that it has the opposite mass, or the same mass as the particle, an opposite type of charge. So a positron has the exact mass of the electron, and the same magnitude of charge as the electron, but it's the positive instead of the negative. And it's a similar case for quarks, which end up to have color charges. So later I will discuss the basics of quantum chromodynamics and how color charges can have a red, blue, or green charge. Then antiquarks can have anti-red or anti-blue or anti-green. So when a particle and antiparticle, their corresponding antiparticle collide, what can happen is they annihilate each other and create photons. So this will also be useful later to note when I go over a basic Feynman diagram. So later on, towards the end of the 1960s, they were able to discover that the proton wasn't actually a fundamental particle as well. So then, hence, all the other particles that were discovered during the particle zoo era weren't fundamental particles either. They were what are called, a lot of them are what are called hadrons, which are separated into two groups. There are either baryons or mesons. A baryon is made up of 3 quarks, and a meson is made up of a quark-antiquark pair. So either, for example, an up quark and a anti-down quark. It doesn't have to be up quark and an anti-up quark. So the method used to discover this was called deep inelastic scattering. So they shot particles like electrons at protons, and then they discovered that the proton had 3 distinct scattering centers, and this showed evidence towards it not being a fundamental particle. So as a result, we learned that all of these are not fundamental particles, and they're actually made up of particles called partons. So there are 2 types of partons. They were the quarks, and then there were the gluons inside these baryons. So the quarks, which were the up and down quarks, which were discovered first, carried charge, and then the gluons, which stuck them together, didn't have any charge. So quarks come in a variety of flavors, and these were discovered as time went on. Eventually it was up and down quark. So a proton consisted of 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. And then you get the various other types of hadrons, which can be consisted of charm and strange and top and bottom. Top and bottom were also called truth and beauty, but I think they kind of abandoned that because it was dumb. So yeah, the standard model has these particles. The quarks experience something called the strong force. which is one of the four fundamental forces, and I will explain somewhat briefly about the strong force towards the end of the talk. And leptons don't experience the strong force. And then your force carriers, or your gauge bosons, they mediate forces between these leptons and quarks. So gluons are said to mediate the strong force. A photon mediates your electric forces, and then the Z and W bosons mediate the weak force. And the Higgs boson is it's hard to explain. It's a type of particle that results from an excited state of the Higgs field. And the Higgs field is a field that can generate mass for certain particles, such as the Z and W bosons. So before I move on a bit more, I want to speak about some of the basics of quantum mechanics and then quantum field theory. So yeah, quantum mechanics and quantum field theory in a very small nutshell. So, so then, okay, a brief explanation of quantum mechanics. So the idea of quantum mechanics is to describe particles as waves and a superposition of certain states. And then when one takes measurements of these states, they collapse into one of the states that they're in a superposition of. So the easiest way to explain it is through this scary cat. So initially, like a quantum particle, when we have not measured the cat in the box, it can be said to be in a superposition of being both dead and alive. So it's both dead and alive at the same time. And then when we take measurements, it has to kind of force itself into a state. In this case, it is unfortunately alive. So yeah. So this rule applies to all quantum particles, and the reason why we don't experience this at larger scales is simply because the deviations would be too minuscule to detect. So quantum mechanics allows us to express particles as waves. However, in order to express waves as particles, we can go into quantum field theory. So the basic idea of quantum field theory is that it's a field theory that meshes special relativity and quantum mechanics. So a field theory is simply a theory of a field and how that field interacts with matter. So gravity, for example, is a field theory. So what else? I mean, that's pretty much all I can go over with regards to quantum field theory without going too much into the mathematics of it all. Let's see. So, however, I can give a brief idea of how particles can interact in quantum field theory. So this is a basic Feynman diagram. And time runs from left to right in this diagram. So what it's basically saying is that we have an electron, that's the E. We have a positron, which is the E bar. Feynman decided that antiparticles should run backwards in time. So we get this arrow running backwards there. And they collide and annihilate one another, and they create the photon. The photon then goes back into creating a muon and anti-muon pair. And that's the basic idea of the Feynman diagram. The reason why we can't have a direct interaction between your electron and muon fields is because that actually creates a non-normalizable type term in the theory itself. So what that means is that we start to get infinities in the mathematics, and then that's bad because then we can't actually use it. So that, I think I suppose that gives you a basic idea of some of the interactions that can happen in quantum mechanics. So with that idea, there are a few quantum field theories. Quantum chromodynamics is a quantum field theory. That's for the interaction of the strong force. So it explains how the strong force interacts with matter. There's also quantum electrodynamics, which explains how the electric force interacts with matter. So I'm just going to go over quantum chromodynamics because it's the more interesting one. So let's see. So as I said earlier, the quarks are pretty much the only ones that experience this force. They experience it inside your hadrons. And what happens is that the quarks either have red, blue, or green charge. And what has to happen inside a hadron is that the hadron itself needs to be white or color neutral. So how it does that is that if it's a baryon, where it consists of 3 quarks, each quark has to be red, blue, or green. So you have to have 1 red quark, 1 blue quark, and 1 green quark. And then they all mesh together and create a white, which is then allowed to exist as an isolated particle. For a meson, which is a quark-antiquark pair, what has to happen is that the quark will have, for example, a red color, then the antiquark will have to have an anti-red, which is also a color. So that's the idea. So we can't actually get isolated particles where they have a color that isn't white. So if we attempt to, what we'll do is we'll put in energy into our hadron in order to stretch or like pull apart your quarks. So the unique thing about the strong force is that as you start pulling apart these quarks, the force actually increases instead of decreasing as the electric force would do. And we can start putting in more and more energy And what will eventually happen is that the system will say, okay, well, you're putting in so much energy, we're just going to create another quark-antiquark pair. And this quark-antiquark pair allows you to effectively create another hadron, a meson. So you've then got your hadron, which might have been a baryon or a meson, and then you've created another meson, which has exhausted all the energy you've now put in. So you got nowhere. And that's pretty much all I can explain about the strong force without going into any math. And yeah, that's pretty much it. Talk done. Yes.
Is an anti-neutron light or anti-light?
An anti-neutron.
So a neutron made up of two anti-down quarks and an anti-up quark. Is that light or anti-light?
It's color neutral. It's like the electric charge being 0. Yeah. Yeah.
What causes charge at like a quark?
What causes charge? The gluons and the quarks, or
so the gluons and the photons, they don't have charge, but the other quarks have strange charge, charge.
yeah. So the gluons, the photons, the boson, the Z boson, W boson, aren't actually quarks. They're called gauge bosons. So gauge bosons are force carrier particles. And the photon doesn't have a charge. What actually is somewhat unique about quantum chromodynamics is that the gluon does have a color charge. It has 2 color charges, actually. It has a normal color charge and then an anti-color charge, which results in the gluon interacting with itself, which can't happen with the photon. So I showed you a Feynman diagram of how the photon can interact to create this particular annihilation. What can happen with the gluon is that you can have these extra interactions here. Like that. So then the gluon actually creates interactions with itself and then goes on to do whatever. So yeah.
What triggers this? Like some trigger or happen?
Triggers as
Interaction that causes the electrons to make a boson.
well, it's I mean, it's just like, I guess, in the mathematics. I'm not. Yeah. And then. Yeah. Yeah. And then the reason why you can create a muon anti-muon is because you can have the photon couple to, or the photon field, it can couple to your electron field and your muon field. And then through that interaction, you're able to create muon anti-muon pairs from electron anti-electron pairs. Yeah, yeah, yes.
Excuse me, you mentioned when you first introduced this slide of the diagram, you mentioned something about time direction.
Yes, yeah.
So when you, and I think you said the direction on this diagram was that
Yeah, time goes that way, yes.
So when you drew on the second diagram, you just drawn the board, when you make the extra squiggly.
Oh, yes, yeah.
Back, does that mean the thing, this is going to sound really stupid, I have nothing in physics, I'm just like, but does that mean the thing goes back in time? What does that mean exactly? Are you misinterpreting this diagram?
No, not it. No, not really. I think it's more like there's a lack of other ways to draw that symbolically. So, yeah.
Is that a product of what happens when it's passing with its normal matter self and antimatter self, and it just changes the direction it looks like it's going into time? Okay, so we don't know what's happening there, it's just something.
Yeah, well, it creates these extra interactions, create extra terms in your in the mathematics itself, and these extra terms actually result in your force growing linearly with the distance between the quarks. So you actually can have an interaction like this as well. Yeah. You just get a whole mess of how color charges interact with each other, or how gluons interact with each other through the fact that they have color charge themselves. Yes.
So.
Okay. Yes.
I was going to ask about that model. The Higgs boson is versus the scalar boson of copper. What makes the Higgs boson scalar?
The Higgs boson doesn't exactly carry any sort of force with it. So usually gauge. So usually these force-carrying bosons shouldn't have mass, right? However, it turns out that the Z and W bosons do have mass. And one of the ways they solved this problem was by introducing a Higgs field. And the Higgs field has something called symmetry breaking, which means that you get a type of vacuum expectation value that is non-zero. Which means that the lowest energy doesn't seem to be zero, I suppose. And because this Higgs field actually interacts with the Z and W bosons, it creates mass terms for them. The Higgs field, okay, so in general though, in quantum field theory, particles themselves are considered excited states, so non-ground states of their corresponding fields. The Higgs boson is an excited state of the Higgs field. And it doesn't, and because of that, it doesn't really, the Higgs field isn't exactly how do I say, it's not, I suppose it's not like a type of field that couples two particles together. Yeah. Can't really give much more of an explanation aside from it being an excited state of the Higgs field. Yeah. Yeah.
With the terms of the gluons interacting with themselves being a part of the what makes the strong force grow with the negligible distance, or is it something along those lines with this?
Yeah.
Does that imply that if you had to take if you had to take your your quarks, like if you had two quarks that are being held together by a gluon, you had to bring them far enough that the strong force reaches its like because it drops off significantly off.
Well, the thing is that we don't know if it drops off or not, because before it drops off, it's creating another quark-antiquark pair.
Okay.
Well, this hasn't directly been proven, but we've done calculations through lattice QCD, or lattice quantum chromodynamics, to show that this seems to be the case.
Okay, so my question was going to be, if you had to take those quarks far enough away, would those terms disappear? So then I suppose the answer is you don't know.
Yeah.
A fair philosophical question that I think ties into the question on charge and the question on ion electron pair annihilates. So if you look at the standard model now, 100 years ago, before Chadwick said that the atom was a believable, that's a solid thing. And then it's like, it's got structure, it's like inside of the protons, or the first protons and neutrons and atoms. Now we're saying actually it's inside the proton, you can posit other things called quarks.
Yeah.
What I'm really curious about is whether there's a limit on that, in the sense of my way of explaining could be a type of causal theory. So if you asked the scientists 2,000 years ago, if I push a box and the box moves, and you said, what caused the box to move? I'm sure a scientist would have said, well, you pushed it. And 2,000 years ago, if you said, why? Why does pushing it cause the box to move? I feel like that would be an incoherent question. Whereas now we can say, no, the box actually moves. We have a causal theory. We can say the electrons on one hand and the electrons in the box, they repel each other, and therefore the box moves. So we can go like a causal theory down. So that's what I heard now when someone said, but why does the electron positron annihilate? Or why, at the moment, it feels like we don't have a causal theory underlying that.
Yeah.
But do you guys, in 2,000 years, do you feel like it's quite possible that we have causal theories underneath all of these things? Or do we have reasons to believe that we've actually reached some sort of deadlock?
I feel like we've reached a deadlock.
Why? Comparing yourself to the scientists 2,000 years ago, like, is there any reason why we can be now reached a deadlock?
I suppose if the last thing we need to do, as far as I know, is try and get gravity quantized, right? So if we're able to do this at this level, I would be quite confident that we've reached the deadlock in that case. However, if we somehow find that there's an even more fundamental structure that might actually help in the unification process. I can't really give much more of an explanation, I suppose.
So you're saying the quantum quantum theory of gravity, if quantum gravity works, then we may say the restriction of everything. So.
Yeah.
Can you maybe say something on if the time axes were on the slides that you had just now?
So is the time axis we're printing up
Yeah.
to this?
What I thought is that would correspond to an interaction mediated by the photon field being plotted from
It sounds.
Does that work?
You have two positive particles and it each other through the state of charge.
I'm just thinking, is that charge conservation correct?
We will have to relabel the particles. It's
Yeah.
This way,
Yeah.
particles go in at that point.
Yeah. I will. Yeah, I'm not sure. I'll have to double check. Sorry? Yeah.
So you said the gluons have two color charges at the same time, is that right?
Yeah.
So are these sort of separate entries, all right? Gluon as a function of some parameters of these separate entries? Or is it a superposition of two different things, like the...
No, these are separate entries, separate, yeah. And then, I mean, you can, similar to all of these composite particles as well, you can have superpositions, in which case, for example, let's see, a example of a meson with a superposition would just be the pion zero meson, which has a superposition of two up quarks and up quark, anti-up quark, and a down quark, anti-down quark. So you can have that in with mesons, baryons, and then you can get similar ideas with the gluons as well. In fact, when you start creating your SU3 group for the mathematics itself, the generators are usually superpositions of the red and blue and etc. Yeah. Sorry? I have to admit, I don't know much about the graviton. Spin 2?
Believed to be massless.
Okay, yeah.
We have some good bounds on the rest mass of it. So there's actually a whole school of research called massive gravity, in which people assign non-zero rest mass to the graviton. It's very complicated. They run into problems in almost every branch. They've got to break some axiom and go somewhere else. It's one of these modified theories of gravity. But what we do know is gravitational waves seem to travel very close to the speed of light, and put very strong bounds on that, which implies that the force-carrying particle, i.e. the graviton, is very close to being massless.
Yeah,
So, for
okay.
instance, the photon is massless, and that's related to the fact that the electromagnetic force is infinite range. As soon as the boson mediating the force has got a rest mass, that force can no longer be infinite.
Yeah.
Extent. So, yeah, a massive graviton would apply on limits to the range of gravities.
Yeah.
Do any of the bosons other than photons decay?
I mean, I wouldn't say. I mean, okay, bosons are also can also be composite particles as well. So the pion 0 is a boson as well. Mesons are bosons. So yes.